All right, here we are moving even further into chapter 15. So far, we've talked about carbohydrates in general. We've focused on the Fisher projections and the Hayworth structures, and even just the chemistry, chemical properties of carbohydrates. And so far, we've focused mainly on the monosaccharides. Here in this fifth lecture of chapter 15, we're going to finally start to give some attention to the disaccharides. So monosaccharides, of course, the simplest. Disaccharides, a combination of two monosaccharides, and therefore slightly more interesting, although maybe slightly more difficult as well. All right, so looking at disaccharides, of course, we don't want to hurt any disaccharides' feelings either, but there are more important disaccharides than others. And so first of all, as a reminder, a disaccharide consists of two monosaccharides linked together, and when two monosaccharides combine in what's called a dehydration reaction or a dehydration synthesis, we get the product to be an acetal and water. So if you look at our important monosaccharides, remember we had glucose, galactose, and fructose. Those were our three most important monosaccharides. Well, guess what? Those are the three monosaccharides that come together to form our three most important disaccharides. So if glucose combines with another glucose molecule, we get those two monosaccharides to form the disaccharide maltose, plus of course the H2O that's split out for the dehydration reaction. For a glucose and a galactose to form, that makes lactose plus H2O. So lactose is the milk sugar, and then it's broken down in the body to glucose and galactose. Most of the time, of course, if you're lactose intolerant, it means you lack that enzyme, or at least lack sufficient amounts of the enzyme to break it down enough, and you get, unfortunately, usually diarrhea, gas, bloating, that sort of issue. For if a glucose molecule combining with a fructose molecule, that gives us sucrose, our good friend, good old table sugar, which seems just about the right sweetness for humans. Fructose itself is a little sweeter, and that can be pleasant or unpleasant depending on how sweet a tooth you have. But sucrose is just about right. It's what most people are looking for. Glucose is not as sweet. It's sort of an unpleasant flavor for most people. But sucrose seems to hit it just right, and that tends to be the one that most of us enjoy as table sugar. All right, let's talk a little about maltose first. Maltose is a disaccharide, and it's commonly known as malt sugar. You can also probably see malt vinegar, which is an oxidation product of that. Back in the old days, when you'd go to the drugstore for a malted, that would be a drink made with malt sugar. There's malted milk balls. Some people like that taste. It's not as sweet as sucrose, but it is an appealing flavor. It's obtained from the hydrolysis of starch, generally wheat starch, and it's linked by an alpha-1,4 glycosidic bond between the alpha hydroxyl group on carbon 1 of the first glucose and the hydroxyl on carbon 4 of the second glucose. It's commonly used in cereals, candies, and brewing, right? Malt will often be seen in beer. And then finally, it's found in both the alpha and beta form. So we'll have to look at this in the next slide to get a better sense of these structures when we talk about glycosidic bonds and alpha and beta forms. Okay, so if we look at these Hayworth structures, looking at alpha D-glucose and alpha D-glucose coming together to form an acetal, right? So we take the OHs and we eliminate a water and form an O-COC linkage there, just like we said we do with any acetal, whether we were talking about specifically things like carbohydrates, or if we were talking about aldehydes and ketones in the previous chapter. This is acetal formation at its finest. And notice in both cases we have an alpha anomer, right? The alpha anomer is the alpha D-glucose on the left and right, but it's the one alpha, because of the alpha anomer on the left, we form the alpha 1,4 glycosidic bond, and that 1 and 4 refers to the carbon number 1 of the alpha D glucose on the left, forming an ether linkage through that bridging oxygen with carbon number 4 on the alpha D glucose to the right. And of course, we also still have the alpha anomer because in the carbon number 1 of the right side alpha D glucose, it's the alpha anomer. So this is actually alpha maltose, which is again a disaccharide. Okay, looking at lactose in a little more detail, lactose is a disaccharide of beta D galactose and alpha or beta D glucose. So it contains a beta 1,4 glycosidic bond, and that's because of the beta D galactose. It's found in milk and milk products, and it's found in both the alpha and the beta forms. And of course, either one will give trouble to people who can't digest that beta 1,4 glycosidic bond, and unfortunately that tends to happen to all of us in old age, but it tends to affect certain groups in even earlier age. Okay, so looking at this image where we see the structures of beta D-galactose and alpha D-glucose, notice beta D-galactose has the OH group up above the ring, whereas the alpha D-glucose has that group down below the ring for both the 1 and 4 position here. The beta glycosidic linkage happens because of the beta D-galactose, so that carbon number 1 having the beta, the OH group above the ring, gives us a beta linkage, that 1, carbon 1 and carbon 4 of the neighbor, so carbon 1 of the galactose and carbon 4 of the glucose form an ether linkage through that bridging oxygen and eliminate a water, of course, an acetal formation, just as we've always done, starting back in last chapter. And then finally, we have the alpha anomer because carbon 1 of the alpha D glucose is the alpha anomer because the OH group is down below the ring. So this is alpha lactose, which is a disaccharide. Okay, now finally sucrose, our good friend table sugar, is obtained from sugarcane and sugar beets, and it consists of alpha D-glucose and beta D-fructose. So it has an alpha beta 1,2 glycosidic bond, and it's hydrolyzed in the body by the enzyme sucrase, and we'll talk about enzymes in a later chapter, but notice it tends to be pretty easy to name enzymes because what they work on just gets an ASE ending, so sucrose, we lose the OSE and make sucrase the ASE to reform the glucose and fructose that came together in the first place to make that sucrose. Okay, so if you look here, we've got something very interesting and different. We have the alpha D glucose and the beta D fructose coming together and forming that sucrose by forming an alpha beta 1,2 glycosidic bond. So notice before we were talking about either alpha or beta 1,4 bonds, glycosidic bonds. In this case, it's the carbon 1 of the alpha D glucose that forms the glycosidic linkage with carbon 2 of the beta D fructose. So we form that sort of bridging oxygen ether type linkage, which is an acetal, to form the alpha beta 1,2 glycosidic bond. So very different disaccharide formation than the other disaccharides we talked about, the lactose and the maltose. But again, it does tend to give a nice sweet flavor to foods and drinks, and that's why we tend to really love our good old cane sugar, which is sucrose. Why don't we pause here for a learning check? In this learning check, you're asked to draw the Hayworth structures and give the names of the two monosaccharides that form when sucrose is hydrolyzed. So in the previous slide, we just talked about the formation of sucrose. So what happens when sucrase in the body converts these things back into the two monomers, monosaccharides, glucose and fructose, that they were formed from. Stop the video here while you draw those structures, and don't forget you're adding a water, so that's going to be the source of the additional H's and O for your two monosaccharides. Good luck. Okay, and there we have it. Hopefully it was a pretty simple task for you. So we take that oxygen that's bridging these two structures in that acetyl linkage, and we go ahead and break it up, and whichever carbons there, in this case carbon 1 of our glucose and carbon 2 of our fructose, get an OH group where we had just that O linkage. So there we have now the alpha D glucose reformed and the beta D fructose reformed, and hopefully that was pretty simple and straightforward for you to do. If not, please do go ahead and try some other um, breakdowns of the disaccharides to try to reform their monosaccharides, and then certainly reach out to me for help if necessary. All right, I've already mentioned a couple of times that sucrose just seems to be just right for us. I'm a big fan of sucrose, if you can't tell. I'll probably pay for it in my later years, but sugars and artificial sweetness all differ in their sweetness values, and they're all compared to sucrose, table sugar, which is assigned an arbitrary value of 100, sort of meeting 100% of what people are looking for in a sweetness. So as you see, we've got some other values here. Galactose is not very sweet tasting at all. It's got a 30 out of 100. Glucose about 75. Again, not quite right, which gives it an unpleasantness for anyone who's had to sit through the glucose tolerance test. Fructose is actually much sweeter than sucrose and actually can be sickly sweet. Some people don't like honey because of the high fructose content. Certainly the high fructose corn syrups that are commonly used in sweeteners give that sort of sickly sweet flavor. If you've ever had Coca-Cola from Mexico, you may have noticed a difference. They still use good old plain sucrose, whereas we here in the States use high fructose corn syrup, and some people swear by it. They love the Coca-Cola made in Mexico because it's made with cane sugar, the sucrose, that just tastes better. The high fructose corn syrup is too sweet for us for whatever reason. Lactose is really not very sweet at all, as we see 16. Maltose is pretty low as well at a 33, and then there we have sucrose, my favorite, the reference standard. If we look at the sugar alcohols, they're again pretty sweet. Sorbitol or glucatol, the most common one that you'll see, 60 out of 100, not too bad. Maltitol there is maltitol, I should say, is 80, and then xylitol is just the right sweetness as sucrose, but as I mentioned, these sugar alcohols have their own host of problems. They can give people gas, diarrhea, unpleasantness to say the least. And there you see some artificial sweeteners, and the artificial sweeteners are much, much sweeter than sugar, plain old table sugar that is. Aspartame, which is actually 2 amino acids. You wouldn't expect that to be sweet at all, but it's 18,000, which is quite a bit higher than plain old sucrose. And then we see saccharin, sucralose, neotame. These are much, much sweeter, so typically much less is used. Makes it tough to cook if you're doing any baking with these artificial sweeteners because you use so little, you don't get the right volume for the recipe. So that's why a lot of baked goods, things that ordinarily would use the sucrose that we know and love, they just don't come out right when you use these artificial sweeteners because you can't use the same amount, and then it just doesn't do the other function of the sucrose, which is to give some bulk and some structure to those sweets. If we look a little more closely at sucralose, sucralose is made from sucrose, so sounds good, right? It's made from that natural sugar that we love, so unfortunately it's made by replacing some of those hydroxyl groups with chlorine atoms, so that's not necessarily the most natural way of doing things, but again, it does give a much, much sweeter compound, and something that for those who are calorie conscious, this is not something that we humans or the bacteria in our guts have much ability to work on. So that's actually been a very popular sweetener as a result, although some people are a little concerned about those chloro groups and they may stay away from sucralose for that reason. Okay, before we leave this second to last section of chapter 15, let's stop for a learning check. And this learning check, we're going to identify the monosaccharides in each of the following. So we talked about our three most important disaccharides, and if you remember, they were comprised by those three most important monosaccharides. So go ahead and tell me what makes up lactose, maltose, and sucrose. Pause the video here if you need a little more time and start it back up when you're ready to check your work. Okay, so there you have it. Lactose is comprised by A, alpha D glucose, and B, beta D galactose. Maltose, number two, is two molecules of alpha D glucose. So just A, but two molecules of A there to form our maltose. And then finally, sucrose is A, alpha D glucose, and B, beta D fructose. So hopefully you were able to do that quite well. It's unfortunately not one that I can tell you to do more practice or reach out to me for help. It's pretty much memorization that maltose is a disaccharide comprised by two glucose molecules, of course alpha D glucose, the form that we would find. Lactose is comprised by alpha D glucose and a beta D galactose. And of course, lactose being in there, if you remember that all three of these important disaccharides have glucose as one of the monosaccharides. In the case of maltose, it's both of the monosaccharides. Hopefully you would know that the galactose therefore goes with lactose and the fructose goes with glucose to form sucrose. Hopefully that helps if you did have any trouble, but that's about the last trick up my sleeve to help you out here. Hopefully you've got these memorized by now or will be able to commit them to memory by exam time. Good luck. See you next time for the last lecture in chapter 15.